Alright, moving on to Unit 2. Unit 2 is all about logic and proof, right? It's all about being able to give evidence or prove your answer. It's not enough to have the answer, you have to be able to prove it, right? So we start with inductive reasoning. Inductive reasoning is making a conclusion based on observations and patterns. So 2.1 is inductive reasoning, making a conclusion based on observations and patterns. All right, we observe the world around us. We figure out the patterns, even if it's unconsciously, and then we use this to make life decisions. Right? We drive on the right side of the road when we're out because that's the pattern. Other people are driving on the right, thus we must drive on the right. That's the pattern, and we use it to keep ourselves alive, right? After you've made your observations and you've recognized the pattern, then you can make a conjecture. A conjecture is like the math form of a hypothesis, right? It's a guess, but not just a guess, an educated guess, because it's based on observations and patterns, right? So a conjecture is a concluding statement reached using inductive reasoning. Right, so once you have observed the patterns and you have made sense of them, then you have to be able to explain them. It's not enough to know the answer, you have to be able to explain the answer. The conjecture is your educated guess, your hypothesis. Educated guess. It doesn't mean it's always right. An educated guess is still a guess, right? It's just based on facts, observations, patterns, right? But it's still just a guess, which means it could be wrong. So if it's right, you have to prove it. And if it's wrong, you have to prove it, right? So it says directions, find the next 5 terms of the sequence, then write a conjecture. All right, so first we have to figure out the pattern between these numbers. And whatever pattern we discover has to apply to all 4 numbers. It has to work for all of the numbers, right? So how do we get from 38 to 31 to 24 to 17? We're obviously going down, but by how much? From 38 to 31, we went down 7. From 31 to 24, we went down 7. From 24 to 17, we went down 7. It's a repeated pattern, so we can keep using it, right? It may have more than one pattern, and that's great. As long as you can defend your pattern, as long as you can explain your pattern, right? Sometimes it's just easy to find the simplest pattern because, well, why would you want to make things more difficult if you don't have to? All right, so 17 minus 7 is 10. So now that we have the pattern, we're going to continue the pattern, right? Minus 7 is 3, minus 7 is negative 4, minus 7 is negative 11, minus 7 is negative 18. All right? Discover the pattern, repeat the pattern, and then we have to explain the pattern, our hypothesis, our conjecture, right? So, subtract 7 from the previous number. That's the pattern. You have to be able to explain it. If you can't explain it, you better figure out a way. Subtract 7 from the previous number. Subtract 7 from the previous number. As long as you can explain the pattern, it's correct. right? And remember, a pattern is repeated. It has to repeat. All right, 2 says 2, 5, 11, 23. Let's see if we can find a pattern for those numbers. 2 to 5, we're increasing. What else do we know? 2 to 5 goes up 3. Then we go from 5 to 11, which is 6. We went up 6. So we could be using multiples of 3. But then to get from 11 to 23, we went up 12. So we can't be using multiples of 3 because we missed 9. Right? So we have to readjust our hypothesis. Right? 3, 6, 12. 3 doubled is 6. 6 doubled is 12. So we're doubling. We started with 3. We started by adding 3, and then we doubled it every time. Let's see if we can continue that pattern. All right, so double this will be 24. So add 24. Now we have 47. And then add double this, which is 48, which is 95. And then we double this, and we get 96. There's another pattern emerging. These numbers are consecutive. 2, 3, 5, 6, 11, 12, 23, 24, 47, 48, 95, 96. There's a whole other pattern emerging. It might be easier to explain this new pattern. It might be easier to use this new pattern. So instead of doubling 96, first we have to add these together. Gives you 191. Instead of doubling 96, we could just go one number higher. We could use the consecutive number because that's the new pattern, right? Our consecutive number is 192. It's the next number. That seems a lot easier. Add them together, we get 383. Then the consecutive number, 384. Add those together, you get 767. So, which pattern was easier? Doubling it was easier in the beginning, but using consecutive numbers was easier in the big numbers. So let's write both, right? So for the doubling, we said we start with 3, start by adding 3. And then double. Three. Repeatedly, right? The second pattern was add number to its consecutive number and repeat. Right? So two different patterns. Is there another pattern? There is. I can see at least one more. What if you multiplied it times 2 plus 1? 2 times 2 is 4 plus 1 is 5. 5 times 2 is 10 plus 1 is 11. It's going to give you the same numbers. 3 different ways to get there. The question is, what pattern makes sense in your head? Whichever one you can explain is the one you should use. Alright, number 3. 1, 4, 9, 6. Interesting. Let's see if we can figure out a pattern. It goes up. It goes up by 3. Then it goes up by 5. Then it goes up by 7. Wait a minute. 3, 5, 7. Those are consecutive odd numbers. So you could just keep going up by consecutive odd numbers. That would be plus 9, which would be 25. That would be plus 11, which would be 36. That would be plus 13, which would be 49. That would be plus 15, which would be 64. And then be plus 17, which would be 81. Figured out one pattern. How do we want to start? By adding 3. And then add consecutive odd numbers. Whoa. I wrote too far to the right. There we go. Start by adding 3 and then add consecutive odd numbers. 3, 5, 7, 9, 11, 13, 15, 17. The next one will be 19. Right? Right. Is there another way? Did you notice anything about your numbers? 1, 4, 9, and 16? Anything interesting? They're all perfect squares. What's a perfect square? The result you get, right? So if you do 3 times 3, you get 9. 9 is a perfect square because 3 times 3 is 9. It creates a perfect square. 3 times 3 is 9. So the perfect square is the answer when you multiply the number by itself. Right? So let's look at those perfect squares and see if we can use them. This is your first number, your second number, your third number, your fourth number, your fifth, sixth, seventh, eighth, and ninth number. Those are place numbers, right? This is your first. This is your ninth number. Notice anything interesting? Whatever number it is, whatever place number it is, squared is the answer. Maybe that would be easier to use. How would you explain that? So, place number squared. Why would this be easier? Well, first of all, you don't have to add anything, right? You just square a number. 5 squared is 25. Done. Again, the addition might be easier in the beginning, but what if I ask you for the 75th number? What if I ask you for the 75th number? Are you going to keep doing this until you get there? It's going to take you a while. Or you could just square it, right? Because the 75th number is 75 squared. And what's 75 squared? Well, it's a big number. I'm just saying it'll take you a long time to get there, right? So sometimes you want to pick the easiest path, as long as you can explain it. Bonus points if you can tell me the 75th number. Quietly, secretly. Alright, so pause this video and work 4. See what you can come up with. Alright, so what pattern did you notice? It's the alphabet. It's not in alphabetical order, though technically it is because A comes before D, comes before G, comes before J. But it's missing some stuff, right? It's missing B and C here. So in this one it's missing B and C. In this one it's missing E and F. In this one it's missing H and I. Every time it skips 2 letters. That's one way to word it, right? So skip 2 letters after previous letter. Right, so if we follow this pattern, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y. Skip 2 letters every time. Is there another way I could have worded that? Yes. Start at A, and write every 3rd letter, right? So add 3. All right, so if I start at A and I write every 3rd letter, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y. Same letters. It just comes down to how you explain it. Whatever works for you, right? Again, number 5, take a second, look it over, figure out the pattern, and see if you can fill in the blank and then explain it before you restart the video. All right, what did you discover? This is time, which complicates things, right? Because we work in 60-minute increments instead of 100. So we have to figure out how many minutes, because of its time, we're dealing with minutes, passed between 7:30 and 7:55. 7:30 to 7:40, to 7:50 to 7:55. That's 25 minutes. 25 minutes. Now, from 7:55 to 8:20, we have half, because it's 5 to 8 o'clock, and then 20, so 25. Again, 25 minutes passed. So what's our theory? What's our conjecture? Add 25 minutes from previous time. Now add 25 minutes to previous time. Right, so if we added 25 minutes to 8:20, we would get 8:45. If we added 25 minutes, 15 would get us to 9, so 9:10. Add 25 minutes, 9:35. Add 25 minutes, 40, 60, 10 o'clock. Add 25 minutes, 10:25. We just keep adding 25 minutes. 6 is interesting. I can see at least 2 patterns. Again, more than one right answer, you just have to be able to explain it. You just have to be able to explain it. All right, the first pattern I noticed right off the bat, 3.14, 3.14. 3.14, that's pi. What are some more numbers of pi? Does it continue 3.1415? If it continues and it's still pi, then you can use pi as the pattern. 3.141592653 are the first 9 numbers of pi, which would be handy if you wanted to know the 75th number. Again, secretly, give me the answer and I'll give you bonus points. What's the 75th number of pi? You could use the other, what was this conjecture? We used the numbers of pi. You could use the other one, which is that you add the two numbers together, right? You add 3 and 1, and it gives you 4. You add 4 and 1, it gives you 5. You add 5 and 1, it would give you 6. And then you'd have to have a 1. And then you add them and you get 7. And then you have to have a 1. Is that right? 6, 1. Oh, the 1 has to be there. You know, I almost forgot the 1. Add 1, it gives you 6. Add 1, it gives you 7. Add 1. How long would it take you to figure out the 75th number using this pattern? Find the easiest pattern, y'all. So how do you explain this one? Add numbers together. Add first two numbers together. Then a 1. Add next two numbers together. You see how it's getting complicated? If it's hard to explain, the pattern's too complicated. Add first two numbers together. Write the total. Add a 1. Add those numbers together. Add those numbers together. And repeat. Getting more complicated. If it's hard to explain, try to find something that's easier. Find an easier pattern. Now, we were able to do this pattern because this number was blank. So we could put a 1 there and our pattern works. But what if it wasn't blank? What if we couldn't put a 1 there? What if they gave us the 9? What if the original numbers that they gave us were 3, 1, 4, 1, 5, 9? Could we still use this pattern? Let's see. 3 plus 1 is 4. 4 plus 1 is 5. 5 plus 9. Wait, that changes the pattern completely. So if the 9 had been there, it would have been a counterexample. It would have destroyed this theory. It would have meant that the only pattern that works is pi. Right? The only pattern that works is pi. If the 9 had been there. Right? It's called a counterexample. A counterexample is an example that makes your conjecture false. Anything that destroys your hypothesis is a counterexample. And the interesting thing is you only need one counterexample to destroy your whole conjecture. One. An example that makes your conjecture false. Directions. Determine whether conjecture is true or false. If false, provide a counterexample. I'm going to ask you to provide an example either way. If you say it's true, prove it. If you say it's false, prove it. If you don't prove it, then it's wrong. I'm not giving you the points. True or false, prove it. The sum, meaning add, of any two consecutive, meaning in a row, right? 5 and 6 are consecutive, 7 and 8 are consecutive, 9 and 10 are consecutive. Integers. Integers are positive numbers, negative numbers, and 0. They're your number line numbers, right? So think about a number line. In the middle is your 0. To the right is your positive numbers. To the left is your negative numbers. These are your integers, right? So we're adding two consecutive consecutive integers, and they're saying you're always going to get an odd number. Let's try a few and see what happens. Let's try a few. Consecutive equals odd. Add consecutive equals odd. Add consecutive equals odd. I mean, it's only 3 examples, but so far it's true. Unless you can find something that proves it false, you have to go with true. You could try this as many times as you want until you feel comfortable that it's true. If it sounds false, keep trying until you find one that proves it false. Alright, 8 says the product, meaning multiplication, of 2 numbers is always larger than either number. So we're going to multiply 2 numbers, and it's saying that we're always going to get a bigger number than the numbers we started with. So 2 times 4, 8. 8 is bigger than the numbers we started with. 3 times 6 is 18. 18 is bigger than the numbers we started with. Here's where you need to remember your number properties. 1 and 0 do weird things. So if they're asking you to play with numbers like this, play with 1 and 0 and see what happens. See what happens. Alright, so anything times 1, and it keeps its original identity. 3 is not larger than 3, so that proves it false. You can also prove it with 0, because remember, you only need one example, one counterexample to prove it false. Anything times 0 is 0, and 0 is not bigger than 5. So it started out looking true, but when you remember to use something like 1 or 0, right, then you can start playing with numbers and make sure that it's true or false. The product, multiplication, of 2 perfect squares is always a perfect square. Remember, we just talked about perfect squares. Right? 9 is a perfect square because 3 times 3 is 9. Right? So they're saying you can multiply any 2 perfect squares and it will give you a perfect square. Let's find out. Let's start easy. Perfect squares, 5s are perfect squares, and it gives you a perfect square.